Good afternoon, everybody. We're gonna cover this week the second part of chapter 2, okay, which is focused around force oscillation and then some reconfiguration of some of the equations. But just before I do that, I'll quickly recap what we're supposed to be doing in chapter 2. Okay, so it's being familiar with the forms of the solutions to both free and forced, undamped and damped symbol degree of freedom equations, and we're going to focus today on the forced damped version. Okay, so we covered those other three last week. We're also going to look at the how to form the equations into the correct form, depending on what you're being given. Okay, so there are some shortcuts. So last week and the week before we looked at applying initial conditions and then going through the algebra. Well, there's actually some equations that we're going to cover right here, where the initial conditions are, you just place them inside the equation, do the maths, and you get the answer. So, like I said, it actually makes it quite a lot easier. And then talk about for force systems, the amplitude ratio, and how that varies with different driving frequencies, and then being able to move the conditions from one form to the other. Now, last week we sort of focused on this one pretty much. There's a little bit on here, but today we'll finish off all of that. If I go to slide 100. Okay, so force damped oscillation, that's what we're going to be looking at. We have the mass spring damper system, okay, the mass spring of the damper, and obviously X is the motion of the mass, and we're applying a oscillatory force to that mass. And in this case, like I said, it's an oscillation, so we call it cosine F naught cosine omega t. F naught is the amplitude of the force, okay, so because oscillation amplitude 0 to the top, okay, and then obviously the omega that we've got there, there's no suffix, so that must be the driving frequency that we've chosen, okay. We want that to be, it's irrespective of what the system wants to oscillate at, that's the oscillation we're going to be using to drive it. Then if you go through Newton's second law, sum of all the forces is mass times acceleration. So there's our spring force, minus sign because it opposes motion. There's our damper force, which also has a minus sign because it opposes motion. And then we've got our forcing function, which we're assuming is in the same direction as x, okay? Put all the x terms on one side and we end up with this as our equation of motion. Second order differential equation of motion. And what we're going to do is we're going to make some substitutions. Okay, we know that in this form of the equation, you can sort of configure it to be in standard form. Okay, which is what we covered last week, where you divide everything by m, and so out front you've just got x double dot. Okay, then you've got c upon m times by x dot, k upon m times by x, and then f naught upon m. For your force. Okay, and what we've done is we've done a bit of additional things. We've gone through and replaced those terms. Okay, so c upon m we've replaced with 2 zeta omega naught. Okay, because they equal each other. And then notice that my k upon m was I take the square root of that, makes me omega naught, and obviously that sits there. Okay, and what we've done is we've moved to the complex plane. Okay, so this cosine. Okay, on the j sine term, you end up with this here. Okay. Remember, you take the real part of a complex number, you get the oscillation, and that's what we're going to be doing here. But it's a lot easier to take the derivative of this, okay, than it is to take the derivative of the cosine stuff. It's more straightforward. And so what we're doing is we're going to take a trial function, which is also an exponential. Okay, we've got j omega t minus delta here, and that's important because the form of the solution has an omega t minus delta. It could be plus delta. It just happens that's the way we're going to work it. So I take that z trial function, I take the first and second derivatives and I insert it into that equation. Okay, you can follow along with on slide 39. Okay, in the notes. And so I end up with this equation. So I've inserted that a e to the j thing, and like I said, we've got an omega that comes out minus omega squared. There's an omega, and obviously for that one there's no nothing that comes out. Okay. And we've got the force on this side. Now, with a bit of trickery in dealing with logarithms, the ej omega t bit cancels from both sides. Okay, but obviously this is also e to the minus delta, or j delta, and if you divide both sides by e to the j delta, or multiply both sides by e to the delta, it disappears from this side, but pops up there. Okay. And this bit, like I said, you can actually write as a complex number with sines and cosines. Okay, so we replace that with the Euler's relationship. So there's our relationship there. Okay, and you'll notice that on the left-hand side and the right-hand side, there are real parts and complex parts. So the real bits, obviously, are these terms without a j in. Okay, that's a real part, and then also there's the complex parts. So you've got the j sine delta here, and then this term in the middle has also a j attached to it. Okay. And so when you're going through the motions, you've got to make sure that those two bits can be equated. So the real parts, we take just the real parts. Okay, so that's the minus omega squared plus omega naught squared. Okay, times by a. Don't forget the a. That must equal the real part of this equation. F naught upon n times by cosine delta. And then the unreal part, or the complex part, the imaginary part, this bit must equal the complex part of this thing. So again, multiply the a through, and then you've got f naught times by cosine delta. The j's, obviously, they disappear because you've got one on each side. Okay, so you're just looking at the coefficients. And so you've got these two equations. How many unknowns are there? There's two, a and delta. So what you can do now is you can go through the motions and simultaneously going through the, doing the simultaneous equations to find those two unknowns. But I'm not going to bore you with the details because it's just algebra, and we end up with two terms. Okay, this is for the amplitude. Okay, so like I said, you can go through the motions and find the amplitude, and then we also have a term for the delta as well. Okay, so there's those two equations. They're in the notes. I think it's 2.3. No, I don't know what numbers they are. They're in the notes, like I said. So you can solve for those two unknowns. Right, so there we go. So again, we convert that equation back to we take the real parts and convert it back to displacement. Okay, and we know that a and delta are these two expressions. Okay, so now, like the forced undamped case, where a and it was alpha in that case, or I can't remember now. There was an amplitude term, okay, and that was defined by the system and the force being applied. Well, you've got exactly the same thing going on here. This is the steady state solution for a forced damped system. Okay, steady state meaning as time goes off to infinity, we ignore what happens in the beginning with initial conditions. Eventually, this is going to be the form of the motion. Okay. And we know that A is going to equal this lot, okay, and delta equals this lot. And so you've got information about the force here, you've got your f naught and omega. You've also got the natural frequency, which is k root k upon m. Okay, we've also got zeta, so that's the damping ratio, c divided by 2 root mk, or c divided by 2 and omega naught, okay. And so there's characteristics of the system and the force in the amplitude, and likewise for the phase angle. Okay, and so they're now not adjustable; they're defined explicitly based upon the force that you're applying. Characteristics of the system and characteristics of the applied force. If we take a look at the equation for A, what happens for different values of omega, the driving frequency? Okay, and you can go through the motions of looking at some examples. So, what happens as omega goes very close to 0? Okay, if omega goes close to 0, then this term is just omega naught squared. Okay, times to the power of 2, and this term is 0 because that omega is 0. So you end up with f naught m divided by omega naught squared, because it's the square root of the square, okay? And if you, like I said, if you actually apply some of the knowledge about what omega naught squared is, it's root k upon m, the ends cancel, we end up with f naught divided by k. Okay, this whole equation drops down to this value here. Now this is known as what's called static displacement. Okay, and if you think about it, if you rearrange this equation, we've got a force, okay, times by, if you put the k up here, so the force equals the stiffness times by a displacement. That's Hooke's law, yeah? F equals kx. It's just rearranged to solve for the x term in a sense. Okay? So that's what we call static displacement. And that's what happens if you don't shake the system at all. It just sits there on the spring, okay? And obviously any amplitude is going to be a force being applied to that spring. So like I said, if you stick in 0 for omega, and here we get okay, yeah, okay, because you get oh yeah, okay, you rearranged with that. Like, so the equation is slightly different because of the way we've got. That's the alternative form of the equation, which we'll cover in a second. F naught upon K is static displacement. Okay. Likewise for delta, okay, if this term is 0, that numerator is 0, tan inverse tangent of 0, we know it's 0. Okay. So so the delta will also be 0. What about if we start driving the system and we're approaching its natural frequency? So we're driving at resonance. Okay. Well, if you go through the motions there, so we go up here. If we're driving at resonance, this term drops to 0. Okay, and we end up with F naught divided by m divided by 2 omega. Well, those two, that's omega naught squared in a sense, times by zeta. Okay, so you end up with a slightly different setup. You end up with the 1 over 2 zeta here, okay? And often we replace 1 over 2 zeta by q, which we call a magnification factor, okay? The reason why I call it quality is that q could stand for quality, and it's about the quality of the oscillator or the oscillation. Something with very low damping has got a good quality oscillation, okay? Something with very high damping has poor quality oscillation. And that's how this relates. Obviously, if zeta goes up, q goes down, and likewise if zeta goes down, q goes up. Okay? So it's the inverse relationship. But basically, you can multiply the static displacement by multiplied by q, okay, and you end up with the amplitude, depending on your frequency ratio. In the last case, where omega, your driving frequency, approaches infinity, okay, so it gets very, very large, what's on the denominator of that equation is simply basically infinity, so the amplitude actually reduces to 0. The thing's being shaken so fast that it can't actually, there's no time for the inertia to respond, and so you end up with 0 displacement. In those last two cases, it's less obvious what delta does, but basically, as you approach resonance, delta is pi by 2, so it's 90 degrees out of phase. So the force will be applying, okay, and the system will take a little bit of time to respond. So you end up with this sort of situation. Okay, it's 90 degrees out of phase. When omega approaches infinity, it's 180 degrees out of phase. So when the force is going this way, then things actually moving this way, so you end up with a situation like this. So, like I said, that's basically how they respond. So if you were to plot those things, okay, you end up with these two graphs. So we've got here an amplitude ratio, okay, which is basically m equals the amplitude divided by the static displacement. So when the amplitude ratio is 1, the amplitude is the same as the static displacement. Okay. And then obviously as you increase your frequency ratio, which is omega divided by omega naught. So again, 1 you're in resonance, okay? Above 1, omega is bigger than omega naught, less than 1 omega is smaller than omega naught. So driving frequency. You start at 0, you've got static displacement. As you start increasing the frequency, obviously you can see there's a slight increase in amplitude, okay? But as you approach resonance, okay, so you're now my frequency that I'm driving is equal to the natural frequency, you get this big peak, okay? And that's because you're exciting the system at the frequency it wants to move at. Okay, you're giving it, you're exciting it at resonance. Okay, that can lead to problems. Depends on how much damping you've got. You can see the more damping you add, the lower that peak will be. If there's no damping, it all goes up to infinity, yeah? Which is what we saw with the case with the undamped system. Okay, damping will reduce that peak, but like I said, what you can end up doing, depending on what the system is and stuff, you can end up hitting physical limits of what the system can do, and obviously you can reach a point where it destroys itself, okay, in catastrophic manner. It depends on, like I said, depends on what the system's doing. There's all sorts of examples of resonance destroying itself. Sometimes resonance is actually a benefit. Okay, so I did some work many years ago now on wave energy devices where you have a buoy that sits on the surface of the sea, and basically what you wanted to design the buoy to do is to have a natural frequency that happens to equal the waves at most of the time. You know, so there's obviously historic data of wave heights and that sort of stuff, and you can work it out such that if you've got your system that's oscillating at the same rate as the waves, then you can actually maximise the amount of energy you're getting out of it. And there's all sorts of different techniques and things you can do to make it simulate different natural frequencies. But like I said, what we're doing there is we're harnessing the benefit of if you excite something at its natural frequency, you get a bigger amplitude. Okay, but like I said, there's many examples of the of resonance being something that destroys it. You've all seen the Tacoma Narrows bridge collapse. This was a bridge built in the States in the 40s, okay, and they made some miscalculations with the bridge design. But yeah, you can see obviously what was happening. The wind was coming down this valley, and okay, it was exciting the bridge just from the way it was sort of aerodynamically designed. Okay, and it started, when they opened the bridge, they could see it swaying up and down. But then they saw that this torsional mode was coming in, and you end up with not only is it being excited, but you get what's known as aerodynamic flutter as well. And you can see that this bridge is twisting. Okay, and like I said, what happens is clearly the bridge is not designed to support that sort of motion. And it reached a point where the bridge can no longer support it. But that's an example of resonance. But like I said, there's all sorts of examples of that sort of thing. Anyway, so yeah. But like I said, so resonance, like you generally want to avoid exciting it. So, for example, if you're designing an engine mount, you wouldn't want your engine mount to be So I'm going to use these equations that are also in the notes. Like I said, I think it was 2.39 and 2.40. So I'll put them up here: 2.39 and then 2.40. The reason why I'm using them is it's a bit easier and quicker to solve this problem. So, but there's a few things we need to work out. So, in fact, I'll move that down. So I'm going to work out first off omega naughts. So that's root 250. 15.8114. Okay, omega, the driving frequency is 2 pi times by the frequency in hertz, so that's 3 pi, and that comes out to be 9.4248. 9.4248. So omega, so R, sorry.
Just doing it on the that's the same as it was before. It's probably to do with
Okay, so we've got this this format. We need zeta and R. Okay, and so the only thing we need to find now is zeta, which we haven't found. So I'm going to write that down here. Okay, so those are my values that I need. R zeta. Okay, so if I remember them. Probably the new page. So if I
Are you ready? No, you need to. Is it using just stretch so one of these actually oh no.
What do you get here? 0.0829. I think I'm just probably typing it. I've got the damping ratio the same. I think it's just on the right now. It could be. I haven't rounded at all.
So 0.108 is for the value of A delta.
Yeah, you've got 7. He's got to say no.
I'm sure that would just
Square root I got 1.0.1. Oh, I got the same thing. Did you get the same thing as well? I got 0.1080.
Okay, so x of t A. Yeah. Okay, so I should have had another slide with a bit more space, but so the equations I've used are the ones from the notes, so this one and this one down here for the A and delta. Okay, and I've gone through A and I've stuck in the numbers and I got 0.108. Okay, I've stuck in the numbers for delta, which I'm not sure what slide. I got 0.2573. Okay. Because I found that omega naught was 15.8114, omega was 9.4248, okay, based upon the 1.5 hertz. And then I found out R by taking my driving frequency divided by the natural frequency to give me R, which I then stick into these equations.
Yeah, I got that.
That's really weird. Before we move forward, I just want to go back to the pictures. This one here. Notice that delta has got a line between 0 and pi. Okay, 0 and pi. We've got 90 degrees or 180 degrees. Okay, but the thing is that with that equation, so if I go back, I'll go this way. With this equation, okay, if R is greater than 1, so if you're driving the system at a higher speed than the natural frequency, okay, then what's inside here becomes negative. When you take the tangent of that number, you get a negative value, okay, which obviously is outside of the range that delta can be. But so what we need to do is, if R is greater than 1, okay, if you're driving at faster than natural frequency, to deal with that problem is you get your number from your calculator, which will be minus something, and you add pi to it. Okay. Tangent is a periodic signal. Okay, it doesn't look like sine or cosine; it's got a different shape. But basically, there are multiple values of delta that satisfy that requirement. Okay, so you just need to add pi onto it to shift it into the realm that delta should be. Okay, that's basically what.
So you add pi, sorry.
You add pi. If you get a negative value from the calculator, you add pi to it. Okay, it's very important because delta, as I said, needs to be between 0 and pi. Okay, so you can't have a delta value down here, but if you add pi to it, you get a delta value that's in that range. And because of the shape of tangent, because there's multiple values of tangent that satisfy the requirement, one of which will be between 0 and pi. Okay? Okay, so that was forced damped oscillation. We're now going to look at some of the solutions. This solution we've seen before. This is for an undamped, unforced system, free oscillation. But that can be written like this. Okay, these equations are exactly the same line. Okay, but they're just different formats. And A and A1 and A2 and phi feed into those values. Okay, so like I said, there's a weighted link between the two. But basically, it's all based upon this trig identity, sum and difference identity. Okay, when you've got two things that are added together or taken away, then you can rearrange it with this. And if you go through the motions of all the algebra, you end up start applying this identity to this equation. Okay. So we've got A times by cosine of omega t times by cosine of phi, okay, minus sine. And so what you can do is, okay, if I say that A times by cosine of phi is A1, and A times the sine of phi is A2, then you can actually split that up into those two equations. So those equations are the same, okay, based upon that relationship. So that's the free and damped response. For the damped response, we can do the same thing. We had omega t plus alpha. Okay, so that can be equal to A1 and A2, but A1 is A cosine of alpha, and A2 is minus A sine of alpha. Notice the decaying exponential term just sits outside. That doesn't change. Now, why am I showing you this? Well, before I show you why, let's have a go at converting between one and the other. Okay. So if I've got this format. Okay. And I want you to write it in this format. Okay. So I told you what A1 and A2 were, but I'll write it up on the board. Okay. Let's go through and solve this problem.
She thinks I've come to university to study to be a mechanic. Yeah, I did have the heart to be like, yeah.
She doesn't need to.
Yeah. I basically was like, yeah, good point. I might need help with gardening or something. Yeah,
Okay, so you can write it out by going through the motions of conversing, you can get this format of that equation. So if you plotted this equation and this equation, you get the same line. Okay, just a different way of working it. 2.8 is about going the other way, okay? I haven't presented the equations used for that, but let's get further on, okay?
Sorry, can I take a picture of your work picture?
It'll be on Blackboard. So. Now why do we do that? Okay, why do we have the why do we apply that format? Well, one of the reasons is to do with the initial condition. Now, if you remember, we have this equation for x of t. If you stuck in 0, you get a cosine of the angle. In this case, phi. Take the derivative. Okay, with this without the decaying exponential, we've got this equation. You end up with minus a omega naught sine of theta. Okay, sine of alpha. Now the reason why we also know that that's the solution to that equation. Okay, you remember? And the a cosine of alpha was a1. Okay, and a sine of alpha was a2. And so suddenly you end up with those the equations. Okay, so suddenly you can stick these values directly into this equation. You end up with an equation. So if you know the initial conditions and you know there's an undamped free response, there you use this equation. There's your initial conditions, and you get the answer straight away. No need to do any of this sort of stuff. Okay.
I've got work, that's why I'm doing it.
Okay. So likewise with the damp response, okay, you remember this from last week in the tutorial class, going through and solving for this, the equation when t was 0, we have that, okay, and when t was 0 for this equation, we have this whole Maloney, okay, and look, again there's an a cosine alpha here, and a sine of alpha over here, okay, so again you can rearrange the equations, you end up getting another form of the equation. There's a1. Oh, let's go through. Okay, so with a free damp system, which is the things we were doing in the tutorial, okay, if you know the initial conditions, you can just go straight to this solution without having to do all that differentiation. Okay, so instead of having to go through and find a and alpha, depending on what's what happened when velocity when time was 0 and displacement when time was 0. If you go straight to this equation, there's your displacement at time equals 0, and there's your velocity at time equals 0. So go through and work out what those coefficients are, and there's your answer. Okay. And then, like I said, what you can do is then reconfigure that to look like it did before. Okay. It's up to you, but like I said, that's perfectly acceptable. That will produce the line. Okay. So remember the I think what we did with the problem. There was a mass spin damper system where we worked out what the equation was. Well, like I said, if you go straight to this one, you can work it out. Okay. So let's do this one. Okay. So a mass spin damper system is a natural frequency of 0.6 radians per second and a damping ratio of 0.2. Okay. The initial conditions of the system are 5 centimeters at time equals 0 and 4 meters per second, 4th x of t. Okay, so if you go to your notes, look at this equation in your notes, and you'll get. Obviously, you just got to plug it through. Okay, so let's just solve this problem. So that's the equation I'm going to use. There's a few things I'm going to identify up here. The omega naught has been given to me as 0.6 radians per second. Damping ratio is 0.2, so omega d So that's 0.6 times 1 minus 0.2 squared. What's that going to be? 0.6, 1.2 squared, subtract the square root. 0.5888. Is it 5879? Okay, and everything else we know. So we've got x of t, e to the minus, and then we've got zeta, 0.2, 0.6, t, x naught is 0.05. Maybe d 0. And then we've got 4 plus 0.2, 0.6, 0.05, 0.5879, sine.
Yeah.
Okay. That I believe is the correct answer. Okay, so that's okay, so now what I'm going to do, just before I move on to the last thing, which is an example, so I'm just going to go back to this slide, okay? I did mention, like I said, this is the way to go from this format to this format, okay? To go from this way to this way, okay, there's some other equations that I didn't show you. Okay, A is basically the hypotenuse, because this is a bit like we've got a point out here. Well, this is A1, this is A2. Okay, so the length of A is the hypotenuse. Okay, and the angle theta. Okay. Okay. That's how to get the alpha. Okay. So to go from this way to this way, you take your A1 and A2 terms and you pop them in these equations, and you'll get A and alpha. Okay. The reason why I'm telling you this now is that when we do the example, we'll be using these equations. Okay. So I shall copy them, and I shall paste them on the slide. Okay, so here's the example. So a boy riding a bicycle or a lady riding a motorcycle or whatever can be modelled as a mass spring damper system with an equivalent mass difference in damping constant of 50 kilograms is the effective mass, 2,000 newtons per meter for the spring constant and the 200 for the damping constant. Okay, the boy or lady rides the bicycle down a curve of 5 centimeters. Determine the equation that describes the displacement of the boy in the vertical direction. Assume that the bicycle is free of vertical direction before encountering the step, changing vertical displacement. Hence, the initial conditions are 0.05 and 0. Okay, I want you to write the solution in this format. So, remember, I'm going to paste my values up there. That was what I had before. So since we know the initial conditions, x of 0 is x0, which is 0.05, x dot of 0, which is x dot 0 equals 0. Okay, so those are our initial conditions. And so we know that x of t okay, so we're doing what we did before, we just need to find the various terms. So omega naught Okay. So we found the various things we need. This equation, we need zeta for omega naught, okay, and then we need omega d for here and there, okay. And now it's just a matter of putting the numbers in. Eight, 3, 1, 6, 2.
Oh, cool.
0 plus. Okay, there's our equation. And if you simplify it down, this is e to the minus 2t. Okay, so there's our equation. But it didn't ask for that, it asked for the equation in a different format. Okay. Good voice this time. Okay, so we take that equation, we put it up here, there it is. And the other thing I'm going to take, oops, just move that over. The other thing I'll take is this lot up here. Okay, so A this comes out to be 0.0527. Okay, and then alpha
So let's say it's going to be I don't want to look. Obviously, it sounds too good to be true.
Okay, so the solution is in this format.
And the interest, you pay it.
Okay.
Thank you, brother. That makes it so much better.
Okay, so that's the end of my my session. So after studying chapter 2, this is where we should be. Be familiar with the forms of the solutions for free, force, damp, non-damp, liquid systems, and understand how they've been determined. Identify the correct form of solution depending on the problem being posed. So if you know initial conditions, then use those solutions that we just covered. If you don't know initial conditions, or you've got a different form of problem, then obviously use both equations. Understand how for four systems, amplitude ratio varies with different driving frequencies. Helps with the graphs that we looked at, okay? And be able to convert solutions from one form to another using any trigonometric identities, okay? Which is what we've just done. For the problem that we've just done, there'll be a MATLAB file that will also go through the solution to have a look at, okay? Showing that those two signals are in fact the same. Okay? I'll do that.